So what did we do last time? We proved that if f is increasing, so theorem, f is increasing and continuous, then f prime exists almost everywhere. And this was the sunrise, sunset. You take the set of points and you take the set E and you cover it by an open interval and so on. We remember this. Remember what we were doing last time. So d plus equals d minus almost everywhere. Okay, that was this sunrise, the rising sun, the setting sun. So here's a corollary. If f is increasing and continuous, and the reason we want increasing is because bounded variation implies the difference of two increasing functions, so we may as well assume increasing, is increasing and continuous, and bounded just means we're on a to b, so it doesn't take the value infinity, which how can it if it's increasing and continuous? Then f prime not only exists almost everywhere, but is measurable. Non-negative, and the integral from a to b, f prime of x dx, is equal to f of b minus f of a.
There was one where it was less than, right?
This is wrong.
Yeah, it's less than.
This is not true.
It's less than.
Okay? So this is true. This is what we're going to prove. Remark. Is false. Why? Cantor-Lebesgue. Okay? Non-example. Cantor-Lebesgue. The Cantor-Lebesgue function. So you already saw this in your homework, I think, at some point. Mm-hmm. Here's the graph of this function. From 1/3 to 2/3, that's what we would be cutting out. So first you make it 0 at 0 and you make it 1 at 1. 1/3 to 2/3, we're going to have the value of 1/2. From 1/9 to 2/9, you'll take the value of 1/4. From whatever those two numbers are, 7/9 and 8/9, it'll take the value of 3/4. And then you just keep making these little dyadic decompositions. And so at the nth stage, you'll fill it in with linear bits to make a continuous function. In fact, they're uniformly continuous functions. So fn converges to f, which is the Cantor-Lebesgue function. And they're uniformly continuous, so f is continuous. It's increasing. And I'll let you check that it is, it's increasing, it's continuous, it's bounded. Therefore, its derivative is measurable. What is its derivative?
0.
Except on the Cantor set, where it has no derivative, it's flat. So its derivative is 0 everywhere. And when you integrate 0, you can't move, except this function has moved. Okay? So that's why we cannot, using only functions of bounded variation, establish the fundamental theorem of calculus. You would think this is, uniformly, it's like bounded variation, uniformly continuous. What else could go wrong? This. This is your enemy. Okay? So let's prove this corollary, and then we'll fix that into an equal sign. Proof of the corollary. So let Gn of x be f of x plus 1 over n minus f of x over h is 1 over n. For every fixed n, this is a measurable function.
Is that 1 over x plus 1 over n?
This is x plus 1 over n.
Okay, thank you.
This is x plus 1 over n. I'm just using, instead of h, I'm using 1 over n.
It just looks like prime n.
Like quotes.
Oh, sorry. 1 1. Is that any better? 1 over n. Let me make this a 1. 1 over n. Okay? These are all measurable. And Gn converges to f prime almost everywhere.
So where is Gn defined?
On A to B. Oh, on, fine. On A to, well, each one you need a little bit less room. So on each subinterval, okay, on the interval A to B minus 1 over n, each of these converges to f prime almost everywhere, and that happens for every one of these subintervals. So it happens to the open B, and because we're talking about almost everywhere, just put in the closed B. Good. Okay, is everybody happy with that? So, so we know that lim sups of measurable functions are measurable. That's the point. We know that we have already proved, let me see the statement. We have already proved that increasing bounded continuous functions have an f prime almost everywhere. That means this limit does exist almost everywhere. And if the lim sup exists, the limit exists and the lim sup exists, and lim sups of measurable functions are measurable. So that tells us that f prime is measurable. Therefore, f prime is measurable. Why is it integrable? Well, it's integrable if it's bounded. It's a non-negative function. Why is it non-negative? We assumed it's increasing. And non-negative. That's just obvious from the definition. Each of these is non-negative. And so if I put in absolute values, what I want to say is, and therefore integrable. F prime is in L1. What does it mean to be integrable? If you're measurable and your integral with absolute values is bounded, and f is bounded, so the difference of these two things is bounded, then you're integrable. That's what it means to be integrable. Okay? So we have to prove that it's integrable by proving this inequality. Now let's look at this inequality. What do I want to use for this inequality? Fatu. Fatu. Because Fatu, what does Fatu say? What's here? The integral of the lim inf of the GNs is not equal to, is at most, the lim inf of the integral of the GNs. The lim inf for the GNs, well, the GNs not only have a lim inf, they have a limit. That limit is f prime. Almost everywhere, which is all that matters as far as the integral is concerned. And let's look at this. What is the lim inf for the GNs? What is the lim inf of the GNs? So this is lim inf. So let's look at the integral from a to b of Gn. That's 1 over n times the integral from a to b of f of x plus 1 over n dx minus, let's keep the 1 over n over there, f of x dx. And that is equal to lim inf of close bracket. So what is this? This is integrating from a plus 1 over n to b plus 1 over n and subtracting off. So this is 1 over n times, when you subtract these two, you get b to b plus 1 over n, f of x dx, minus the integral of
A to
to a plus 1 over n f of x dx.
We can use the differentiation theorem.
And we can use Lebesgue differentiation theorem. This
Okay, it's like a
converges to f of b, because it's the average value. Lebesgue differentiation theorem. This together with the 1 over n. So, okay, fine. Let's put
Well,
the
why can we use the differentiation theorem? Why do we know that it works for B and A in particular? We just know that it works almost everywhere, right?
Lebesgue integration theorem says that, yes, it works almost everywhere, but f is continuous. So once it's continuous, then it's
Oh,
not an
yeah.
almost everywhere function. It's everywhere.
Yeah.
And this,
That's what we did, right? We approximated by a continuous function in the proof.
in the proof of the Lebesgue differentiation theorem.
Since it's continuous, we don't have to approximate.
We don't have to do anything. And, right, let's recall Lebesgue differentiation theorem. What we proved was something like, if you look at the integral over a ball, and you divide by the measure of the ball, of an integrable function, f, in fact, didn't even have to be integrable, just locally integrable. You remember this? And you take the limit, first of all, the limit exists as the measure of the ball goes to 0. Try again.
Wait, what's the continuous function here?
Big F.
Big F? Do we assume that's continuous?
Yes.
Because the Cantor-Lebesgue function is decidedly not continuous.
The
It's
Cantor-Lebesgue
always
function
continuous,
is
right?
continuous. That's the crazy thing about it.
I forgot. Okay.
So it's increasing, continuous, and bounded, and yet its derivative is 0 almost everywhere, and when you integrate 0, you don't get 1. Okay, so f was increasing. So we're about to prove this statement. We have the integral from a to b of f prime on one side. We're using for 2, so that's a less than or equal to. And on the other side, we're coming up with f of b minus f of a. So that's the completion of the proof of the corollary. And I just want to recall the Lebesgue differentiation theorem.
So what does it say on the right? 1 over n times the integral.
1 over n, sorry.
And why are we writing 1 over n?
We had that out front. And I closed the brackets that I could
It's just
honestly write. It's this plus that 1 over n, so then I just distributed it so that it.
Yeah, but it's just a style not to write n, right?
Yes, it's just to make it look like 1 over the measure of the ball. Because this is the ball that contains b and is zooming in on b, which is what I'm about to recall for you here. It's that if you take 1 over the measure of a ball times the integral over that ball of a function that's locally integrable, and you take the limit, and the limit exists, as the measures of these balls go to 0, and the balls always contain some fixed point x, then for almost every x, this limit exists and is equal to f of x for almost every x, almost everywhere.
So this is maybe like a technical point, but we have to use closed balls here, right, for that theorem? Because B wouldn't actually contain B otherwise?
Yes, and it doesn't matter because
Still bound to B's intrinsically.
the difference in the measure is non-existent.
Yes.
Do we have to worry that it's a limit instead of a I guess it could just be less than or equal
The
to
limit exists, so.
So these limits exist. So the limits are equal to the limits.
Why do the limit exist?
The limit exists because of the Lebesgue differentiation theorem.
Okay,
It exists almost everywhere, but this function is continuous.
got it.
Should we extend big F first, because there's no definition for f b plus 1 over f?
Yeah, just
Yes.
extend it as a constant, and then you don't need any
Sure.
theorem at all.
Fine, extend it as a constant, past b.
Then literally 1 over n times that integral is precisely.
It's precisely f of b. Great.
But the other one, you do, right?
The other one, there you use Lebesgue differentiation. Yeah. I like that. Extend as constant on b to b plus 1. Yes?
For the other integral, I think we can just use f is increasing, because if f is increasing, then the integral is at least 1 over n.
This is so easy. We're like, yes, I agree. There's a million much easier ways. This is like taking a jackhammer to, you know, ping pong. I don't know what the analogy is.
This is true.
It's so easy. With a continuous function, this is true. There's nothing to do. This is like, you know, how crazy of a function could you be to be, you know, L1? All we've assumed is L1. So this is definitely overkill, but I do want to recall this theorem because I'm going to use it in a second. But yes, we need much, much less than Lebesgue. You're absolutely right. This is like, so this is just, you know, this is not a theorem. This is a slight theorem using the continuity. Okay, good. So we clearly need something more in order to be able to conclude equality and not less than or equal to. Okay, and that something more is absolute continuity. So recall, we also proved, yeah, I want to give you a better version. There's a one-dimensional version, but actually what we proved is that if f is in L1, then for all epsilon, there exists a delta such that for all sets E of measure less than delta,
Oh, yeah.
for all measurable E with measure less than delta,
Yeah,
the
less than
integral of f, in fact of the absolute value of f, over E will be less than epsilon.
Mm.
And this was the absolute continuity of the integral. So if you want a function whose which has a derivative, it had better be an absolutely continuous function. So let's define absolute continuity on the real line. So definition, f on a to b is absolutely continuous if let's mimic this. For all epsilon, there exists a delta such that for all, let's say, points, let's call them T1 through Tn. How do I want to say this? I had a better way of saying it. Fine. If for all intervals, so let's say AK, BK, disjoint, K goes from 1 to N. So for any finite intervals with measure of this disjoint union of AK, BK from 1 to N being at most delta, if you, no matter where you are, no matter how many intervals you take, I want not just uniform continuity, I want absolute continuity. It's a horrible term. It's a horrible historical term. So, for any epsilon, there's a delta. So that anytime you have intervals whose measures add up to at most delta, the integral, so f of bk minus f of ak in absolute value, if you sum all of those errors, they come out to no more than epsilon.
Can that be complex, or is it?
F can be complex. All I'm doing is taking absolute values. So if you have a function on a to b, then that's the analog of this, right? So this is a definition which is, well, it's just about finite intervals, but of course you can say much more in the case of integral functions.
Does this say something about the Borel measure that f generates with respect to the Lebesgue measure? Because like the sum on the right is sort of like the measure of those intervals under that measure, right?
Kind of. So one thing you can see just by taking one interval is that f is uniformly continuous. So, remark, absolutely continuous
Right.
implies uniformly continuous, which implies continuous. Okay, so F is definitely continuous, so the pre-image of open sets is open. So say again your question about being Borel.
So if you are in, this is just absolutely, but say that F were like increasing or something.
Yes.
Then you get a unique Borel measure on the real line.
So if it's increasing, then this is, then you get a Borel measure. Either way, so
I mean, still try. It's like, is this like saying the two measures are related somehow? Like, is the Borel measure like absolutely continuous? I forget what the word we used for it was.
yeah, it's kind of saying something like, well, okay, so if it's increasing, let's talk about that case for a second. If it's increasing, then this is basically saying the derivative is bounded. If you want to think about it that way.
Sure.
So actually, a great exercise is to see that the Cantor-Lebesgue function is not absolutely continuous.
Okay.
Why?
Otherwise, it would equal the integral of its derivative.
Okay, but how about from the definition? Yes, that's right. The theorem I'm about to write is that the fundamental theorem of calculus does hold for absolutely continuous functions. If you integrate the derivative, we already know that if you differentiate the integral, that's the Big Differentiation Theorem. If you differentiate the integral, you recover the function. You recover the integrand. Now we're trying to go the other way around. If you integrate the derivative, do you get the function back? And the answer is no if you're just, not even if you're continuous. Even if you're uniformly continuous, the answer is no.
Yeah, the bounded derivative, that was like the Lipschitz exercise.
Yeah, so Lipschitz type, if you want to think about this as Lipschitz, well, if b minus a, if f hasn't moved b, if you have an interval a to b, and whatever f does to that interval, it hasn't moved it by more than a constant, well, then that tells you a linear relationship between epsilon and delta. It doesn't have to be linear. It could be much worse than Lipschitz to still be absolutely continuous.
Yeah.
So absolute continuity is certainly enough. Okay, so a good exercise to think about why, not just that the conclusion would fail, but why Cantor-Lebesgue is not absolutely continuous. Just from the definition. You see why?
Because the derivative is measured zero. So we can use open intervals to cover any intervals which measure is less than delta.
Right.
But then the sum is near 1, I think.
Right. So the point is you can make very small intervals around the Cantor set where the function is doing all of the growth.
Yeah.
So you can't ever, and you can make those intervals as small as you like, and the function will still be having all of its growth there.
Yeah, there's all the increasing and
But
very
it's going to be a
small
finite
numbers.
number of intervals.
Yeah, but you can make it arbitrarily large, finite but arbitrarily large. So we're about the finiteness and disjointedness. We're about to do a Vitali covering lemma about that basically says anytime you have a set of finite measure, you can find finitely many balls that cover it and within delta mass above and below. So in fact, should I do that now? Yeah, why not? Why not? Okay. So our target theorem, let me say that, and then we'll get to the Vitali covering. Our target theorem is that absolute continuity, not only is it necessary, it's enough. It's an if and only if. Absolute continuity completely determines when the fundamental theorem of calculus works. So, target theorem, if f is absolutely continuous, then we already know that, so this isn't the target theorem. Absolute continuity not only implies uniform continuity, it also implies bounded variation. So it's a difference of two increasing bounded functions, has all kinds of nice properties. in particular, we can use the previous results about f prime existing everywhere. Okay? So if it's absolutely continuous, then the integral, I mean, what we really want to say is that the integral from a to anything, including b, is big F of x minus big F of a. Okay, that's our target theorem. Good. So, and this is if and only if. In other words, how do I want to say this? Yeah, let's just leave it like this. Let's just leave it like this, and I'll make a bigger deal about it when we get there. Okay, so let's talk about Vitali coverings. We need to set up the proof of this theorem with a pretty sizable machine. We need Vitali coverings. So definition: given a set, you could do this anywhere where we have balls, so metric space. A Vitali covering of E is a collection of balls B and B such that for every x in E and for every positive eta, there exists a ball with measure at most eta, which covers it.
There exists a ball in the covering?
There exists a ball, so a collection of balls so that for every x in E and every eta, there exists a ball in the covering with measure at most eta and x in the ball. In other words, I just want to make sure that I can zoom in. In a second, we're going to take a very special set of balls, and I want to know that that set of balls is not too special that it looks like what you would think of as just take all the balls that cover a point. So I want to be able to have arbitrarily small balls that zoom in on any point in the set. That's what it means to be a Vitali cover. i.e., can zoom in on any point of E with balls from B. So if you have such a thing, so now let's specialize to RD, because I'm going to use a theorem that we proved about RD in a second. This is for a general metric space as stated. So here's our, I guess I'll call this covering lemma. Covering lemma, which says exactly what I just said. If E in RD has measure finite, so in particular it's measurable. If you have a measurable subset of Euclidean space with finite measure, and B is a Vitali covering, then there exists a finite collection. Let's call it, should I call it something? S? With disjoint balls. And if you take the measure of all of these balls, the measure of this disjoint union of balls in S, that will get you up to the measure of E minus delta. Then for all delta, okay, so the picture is you have some set E, I don't know what it looks like, I'll find finitely many disjoint balls in my Vitali cover so that the measure of these balls is at least the measure of E minus delta. In fact, we can do something a little bit better because this doesn't control, I mean, I can get my measure of the balls to be large by some stupid way, perhaps. You can control not just this size, but the set difference between the two. But for now, let's just say this. Okay? Here's the proof. Very simple. So if you have a finite measure set, remember week 2 or something, we were talking about what measurable sets look like? So the measure of E is finite implies there exists a compact subset. So I drew E as some bounded thing, but in fact it could still be finite and have this cusp out to infinity. There's a compact subset of E with the measure of K being at least the measure of E minus epsilon for any epsilon. Of course, you have to give me the epsilon first. Okay? So so this is vacuous if, this is vacuous unless the measure of E is greater than delta. Or not well, it's a tautology. So delta is going to be less than that. Take epsilon equal delta. Okay.
You have like a cover.
Yeah. That's exactly what I'm gonna do in a second. So so delta is given to us. Just want to make sure I do this in a optimal way. Yeah, let's just make that delta. Okay, so you can do it for any epsilon particular. I can do it for delta. There exists a compact subset. Let's call this K1. K1. So first I cut out a compact subset. Because it's compact, of course the Vitali cover is a cover of K1. So B covers K1, which implies there exists S1 finite. This isn't even the S that I want. Let's call it B1. Let's call it B1. So there's some finite subset B1 covering K. Covering K. K1. We're about to do a induction. It's not even induction, it's just counting. Okay? So we have this set B1, it covers K1, and it's finite. You remember this lemma a long time ago about finitely many balls? Question?
You choose the largest ball and then you take away the ones which intersect.
Exactly, right? Exactly. By old lemma.
The other Vitali covering.
Yeah, did we even call it Vitali? I think we just called it ball covering.
I think we mentioned the word Vitali.
Oh, okay.
Well, I took 32 to the D1s.
Yep.
There exists a subset S1 of B1 of disjoint. See, this doesn't give me disjoint. This will give me disjoint sets. Disjoint balls. With the measure of the disjoint balls in S being at least, so we have to drop a bunch of them, but we're not going to drop too much. We're going to drop being at least, what is it, 1 over 3 to the D?
3 to the D over A.
Well, there was a constant, and that constant is 3 to the D. The measure of all of the balls, the union over all the balls in B1.
I think the 3 to the D was not numerated.
So what we said was you can find a finite subset.
Okay.
Yeah, I want it this way.
Yes.
Okay?
B in S1 or?
B in S1.
Was there anything else to that lemma, or was that it? It was just the 3
No,
to the D?
because remember the proof. You have a finite number of balls.
Yeah.
And what you do is you take the largest one, and 3 times that ball
Yeah.
will cover anybody that intersects it. Throw out anybody that intersects it and iterate.
Yes.
That's the argument.
We're in RD.
This is
where
in
that
RD.
D comes from.
That's where this D comes from. Yeah. We'll only apply it to R1, but let me give you a general, because it's the same. It's the same proof. May as well do it in RD. And it's true in any metric space that has this invariance under, that has this homothety. You scale by something, it scales by something related to the dimension. But we have to talk about dimension on general metric spaces eventually. Not now.
Would you define it by that scaling thing?
Well, that's box dimension, and then that sometimes, but not always, agrees with Hausdorff dimension. And you can have different gauge functions. We'll have some fun with that one of these lifetimes. Okay, so look, we have this collection S1. Okay, if the measure of this union of balls in S1 is already bigger than the measure of the original set E minus delta, then we're done. Then we're done. Otherwise, look at, otherwise, the measure, let me just write this as the measure of S1, meaning the union of all the balls in S1, is less than the measure of E minus delta. And so the measure of E take away S1, how do I want to say this? So the measure of E take away S1, in fact the closure of S1, since the closure has, I just want to include the boundaries of the balls, and the measure of E take away S1 is at least delta. We couldn't have covered more than delta of this difference. Does everybody see that? Should I draw you a picture? You see what's going on? Let's draw a picture. This was E, and then we took some compact subset of it. Well, let's just say E is equal to K, just to make things simple. Then we found this finite set of disjoint balls S1. That's S1.
They are contained in E?
No. They have some pieces of E. Now, if the measure of those balls was already bigger than, if we at least got as much measure as E had, then we stop. If we didn't, then how much measure is left over if we throw out the balls and their boundaries? So how much measure is left over here? Well, there has to be at least delta measure left over. Okay? So what do I do on this set? So let's call this E1. Repeat. Now, there's one thing, which is that if we look at the subset of the balls, I want to make a new Vitali cover of E1 using the Vitali cover of E. So, let me say this.
Is that for shorthand for the union of
Yes.
all balls? Okay.
Yes. So instead of writing all of this, I'll just say this by this abusive notation. Okay? So now we're going to cover this by, again, some balls, some finite number of balls, but I want to use balls that are disjoint from all the balls in S1. So the only thing to observe that the set of balls in B, which are disjoint from all the balls in S1,
This is also a Vitali cover?
is also a Vitali cover, is Vitali cover for E1. Because if I have something that wasn't in the closed,
You could shrink down to it.
you can shrink
There's
down.
only
Yeah, you have some room.
balls.
You have some room. I took away everything in the closure. Okay, so what's left is some open bit. I mean, E itself doesn't have to be open or closed. It's just some random set. But I'll find this compact. So iterate. So then I find S2, which is disjoint and disjoint from S1. So this is a subset of B, finite, disjoint, and disjoint from S1, and disjoint from S1. And two cases. Case one, oh, by the way, I wanted to say here, all the way back here, that the measure of S1, what's the measure of S1? Well, the balls in B1 are a cover for K. And if they cover K, then they cover, not case one, hang on. I need a little bit of room. This is at least 1 over 3 to the d times the measure of K, K1, because the balls in B1 covered K1. I can't have them both. I have the measure of S1 is at least 1 over 3 to the d times the measure of the balls in B1, but that was the finite set that was still a cover for K1. So if that union covers K1, then that's at least 1 over the same constant times the measure of K1. And K1 was chosen by having measure at least.
It was thing minus delta.
Yes. So this is at least 1 over 3 to the d times the measure of E minus delta, which is positive. So every time I do this, I again get a set which has, you see what's left over is, has some positive amount. So every time I do this iteration, how do I want to say this? How do I want to say this? If I haven't iterated enough, right, sorry, that's not what I want to say. I just want to say that the measure of K1 is at least delta. Because if it's not at least delta, let's go back. Let's go back one line. The measure of E is at least delta. So now I don't want to get within, let me replace this by just delta. The measure of E is strictly larger than delta, otherwise everything is vacuous. So if I can get something containing an E that's close to E, well, I can certainly get it. I'm asking much less. I'm asking much less to say this is at least delta.
Yeah, you can do that. Okay. As long as
Just
delta
here.
is strictly less than-
Delta is strictly less than the measure of E.
Okay.
So not only can I get close to the measure of E, I don't want to get close to the measure of E, I just want to get up to delta. All the way back here. Okay? So just give me some delta-sized piece, at least delta-sized piece. Then I'll cover it so that here I don't have to deal with measure of E minus delta. I just want to put delta there. That's the measure of K1.
Can you show the source of that error?
One more time, up here.
Oh,
So all I'm saying is I had a cover, S1, finite subcover. It's not a subcover, it's just a finite subset of disjoint balls in B1, which loses no more than a constant of the mass. A fixed constant independent of anything other than the dimension of the ambient space. This is a cover for K1. This is a cover for K1. And K1, from the very beginning, I don't want to deal with this. I want to just, don't make me get close. Just give me delta size, some fixed delta size.
So wait, I agree this works if delta is strictly less than the measure of E, but what if delta is the measure of E?
Then
you can't get close.
Then this statement is vacuous, because the measure is a non-negative function.
Yeah.
Okay.
Okay? So if measure of E is equal to delta, then this is 0 and there's nothing to do.
Okay.
So I only have something to prove if, so I'm assuming that delta is strictly less than the measure of E. Okay? So far so good? So the point is, every time you do this iteration, you do it under the assumption that the measure of the thing that you're covering is strictly bigger than delta. So now you get a compact subset whose measure is at least delta. So that'll be K2. So let's flesh out this iterate a little bit. Let's flesh out this iterate. What do I mean by iterate? Get a K2 compact subset of E1. E1 has measure at least delta, strictly, because it's the otherwise case. You get a subset with the measure of K2 at least delta. You have this sub-Vitali cover of E1, what becomes a cover of K2, which gives you a collection. So there exists a finite B2 in this Vitali subcover. I don't know what to call it. Let me not call it anything. And that contains a finite S2, which is disjoint. And all the balls in S2 are disjoint from the balls that we had in the first iteration by the construction of this Vitali subset. So we just iterate this.
How are we eventually going to get big enough?
How are we eventually going to get big enough? Every time we do this step, we add delta times delta over 3 to the d, which is independent of anything.
Right.
So we grow by a fixed amount every time. But look at when we stop. We stop when we exceed the measure of E minus delta. We have a fixed uniform bound where we have to stop everything.
Yes. So this will terminate like finitely many steps.
This will terminate in finitely many steps. Okay? So each iteration, right. So stop, halt, if the measure of E take away S1 disjoint union S2 disjoint union SK exceeds, is at most delta. Is at most delta, since that implies that the measure of S1 disjoint union SK is at least the measure of E minus delta. But each K adds, each time you do this, you add each K, each new K adds at least delta over 3 to the d mass to that. A fixed amount of mass. Okay? So must halt after finite time. So algorithm halts after finite time. And the only way to halt is if you succeed. Okay, so you start with your set E. So E. You start with your set E. You get some compact subset. I don't care what it is. It just has to have size at least delta. Then you find some finite disjoint subset of it that has measure at least delta over 3 to the d. Then you look at what's left. And you get some other compact subset. And you cover that. And you look at what's left. And you get some other compact subset. And you cover that. Eventually, you have to get at least the measure of E minus delta of the mass. Because every time you do this step, you gain a fixed amount. And the measure of E was assumed to be finite from the beginning. Okay? In fact, we've proved something slightly stronger. So corollary. Balls can be arranged. Balls can be arranged such that the measure of E take away these balls, this S, this set S, this finite set of disjoint balls that we get at the end, is at most 2 delta. Well, you could rename delta, but let's keep it with the same concept as before. So not only, sorry, what do I want to say? Yeah, of course. All I said initially, all we said here is that the measure of these balls is at least the measure of E. But that measure could have come from most balls being far from E. I didn't say that what's left over has size at most delta. This is saying what's left over has size at most 2 delta. Okay, proof. This is very simple. Let O cover E be open such that the measure of O is at most the measure of E plus delta. Sorry. And replace B by B intersect O. So you have your Vitali cover. Just intersect the Vitali cover, intersect the balls with O. That still gives you balls, whatever balls are inside O. So O is an open cover of E. E is measurable. I can find an open cover which is bounded by the measure of E, which is not too much bigger than.
You just mean the balls that are contained in O, right? Not like the actual intersection of the balls.
I mean that the balls are contained in O by the set of balls in B such that the balls are contained in O. That's still a Vitali cover. Run the argument on them, and so the measure of E, take away this set S that we get from this argument, is at most the measure of O, take away the measure of these disjoint union of B's. Because all the balls came from O. All the balls were contained in O anyway. So that's take O and take away the measure of the B's. And now this is at most. The measure of O was the measure of E plus delta. The measure of the B's is at least the measure of E minus delta. And that's your 2 delta. Okay? Does that make sense? So all we're doing, we got this Vitali cover, and you can make the Vitali cover not just have a nice size, but the set difference will be small, as small as you like. All right, let's prove our main theorem. Arg. Can I have that, please? Oh, it's by me. Okay, so here's our main theorem. So theorem, f absolutely continuous, and f prime equals 0 almost everywhere, implies f is constant. And from that, we'll get this is the usual way of doing it, right? Even in Calc 1. So if this derivative is 0 almost everywhere, then the function is constant. So let's look at proof. Let E be the set of x in A to B such that f prime equals 0. This happens almost everywhere by assumption. Okay, the derivative exists and is 0. So measure of E is equal to B minus A, which is finite. What does it mean that the derivative is 0 for all x in E? the limit as h goes to 0 from above or from below of f of x plus h, the limit as h goes to 0, f of x plus h minus f of x over h in absolute value is 0. In particular, I can make it less than epsilon over any interval. Okay, so let's fix epsilon. Fix epsilon positive. F is absolutely continuous. There exists a delta such that yada yada, f is absolutely continuous with respect to that, such that for all a, ak, bk, so that the disjoint union has measure less than delta implies f of bk minus f of ak in absolute value sums to less than epsilon. God, that's horrible, but hopefully you understand what I mean. So give me any epsilon. F is absolutely continuous. That means there is some delta, so that whenever you get intervals of size, that total size is at most delta, the function has total variation at most epsilon on those intervals. Okay? You've given me that delta. Now, I have this set E. I'm going to make a Vitali covering of E. So I have my epsilon. That means I can make this limit less than epsilon. So take a, for all x in E, and for all small h positive.
Intervals around x or something?
Yes. There exists an open ax bx.
What does small mean?
Well, small enough that I'm not outside of a to b when I do this. So let's make this contained in a to b. So it doesn't have to be small, but just make it contained in a to b when I'm evaluating this thing. And this contains x. So there exists an open interval ax bx contained in a to b containing x such that what? ba minus a bx minus ax is at most h. So I want these intervals to be of size at most h. And because it's of size at most h, I can make this less than and f of bx minus f of ax is at most epsilon times bx minus ax.
And that's just from differentiability.
That's from f, the differentiability being 0. So I can make this ratio less than epsilon by making h small enough. In other words, I'll find open intervals, ax, bx, contained inside a to b. That's what I mean by make h small. I mean, I'm just trying to catch this with an interval, since this is from above or from below. So catch this condition on an interval, it's that f at the endpoints is at most epsilon times the length of the interval.
The roots have something to do with the epsilon, right? Because we are fixing epsilon. So
We're fixing epsilon. We're fixing epsilon from the very beginning.
Yes. So the length h, which might be epsilon.
I want every h.
Yeah.
For every h, I can find an interval of length at most h containing x. Zooming in on x, I need this. My claim is that this is a Vitali cover of E. The set of such intervals is a Vitali cover of E. So let me say that. Claim these intervals are Vitali cover of E.
Can we explain how we get this last inequality again?
Yes.
Don't we need one of them to be x? Maybe I'm a little rusty on like differentiability.
No, because you can go from above or from below.
We're going from both at the same time?
Yeah, so let me put it here. F of bx minus f of x
Yes.
plus, or I guess minus,
Right.
f of ax minus f of x is f of bx minus f of ax. So maybe this is 2 epsilon.
Okay, yeah, sure.
Okay, so you didn't have to go from x plus h to f of x. You can so you have some a that's below x and some b that's above x, and you catch these 2 conditions. And for every single h, I'll find I just need one interval per h of length at most h. So that's zooming in. Why are these intervals a Vitali cover? Because I can zoom in on x, staying inside E. So for every x in E, there is this zooming interval that contains E, and it has this satisfying this condition because the derivative is 0 in E. And E has finite measure. Now we just apply the Vitali lemma and follow the consequences. Okay? So far so good? Let's do it. So what? So what? So this is a Vitali cover. Okay, so by the Vitali lemma says there exists, what does it tell us? We can find a finite collection of disjoint intervals. There exists a finite collection of disjoint intervals covering, coming from this covering. So let's call these intervals I1 through In. So each of these is aj through bj, such that the measure, so the sum of the measures of these ij's is at least the measure of E minus delta, also known as B minus A minus delta. That's the Vitali lemma. Okay? Now let's follow what this says. What does this say? So here's A to B. So we have this interval I1, and here's an interval I2, and here's an interval IN. And these intervals cover all but delta of B minus A. And on these intervals, if you're inside, so this is, let's call this A1, B1, A2, B2, and this is Bn. Okay? What's going on the complement? I don't know. I don't care. Because look at the complement. So complement, in other words, B to A, A to B is how we usually write that. Take away the union over the i's is also intervals. It's a bunch of intervals that look like is a disjoint union of, I guess these are closed intervals that look like what is this, bj to aj plus 1. And let's call b equal to an plus 1, and let's call a equal to b0, so that we can keep this uniform. Okay? So now we're done, I claim. Let's see why. Let's see why. Let's put all of this together. The measure of this complement is at most delta. The measure of this complement is at most delta. And it's a bunch of intervals. F is absolutely continuous. Epsilon and delta were chosen. So the sum of f at this bj minus f of a is less than epsilon when you sum all of the changes.
What were we trying to prove again?
We're trying to prove that f is constant.
Right, okay.
I'm going to prove that the value of f at a minus the value of f at b is less than epsilon.
And we're gonna do like a telescoping kind of thing here?
Well, we're going to do two different things. We're going to do something on the complement, because the complement is small. We're going to use the absolute continuity of f on the complement.
Yes.
On the intervals themselves, they were constructed
To work out nicely.
to work out nicely.
Right.
Okay? So let's look at f of b minus f of a. Let me see if I can do this here. So, f of b
Okay.
minus f of a.
Are we assuming non-decreasing?
No,
No.
nothing about increasing your, yeah.
So this
Just
won't-
absolutely continuous.
This won't tell us that it's.
It'll tell us that, so if I can prove that this is less than epsilon, for every epsilon,
Yeah.
independent of a and b,
Then you've shown that endpoints are the same, or are we?
I've shown that the endpoints are the same and this argument will apply to every sub-interval.
Any pair of points.
Any pair of points, yeah. Yeah, that's right. I could also just take the increasing, if it's absolutely continuous, then it's uniformly continuous, so it's the difference of two increasing functions, so do this for each increasing function. Yeah, if you like.
But each one need not be absolutely continuous itself.
Did I miss that lemma? The total variation is an absolutely continuous function if f is. And so are the positive and negative variations. I had a lemma here, or exercise.
That's all right. No point in looking. No point in.
Remark. Absolutely. Exercise. I missed the exercise. Thank you.
No, don't worry about it.
Thank you. Where can I put this? Where can I put this? Where can I put this? Okay, I'll let me finish this and I'll add the exercise. It was right there. I skipped it. Okay, so what am I going to do? I'm going to take this difference and I'll do minus f of bn plus f of bn minus f. In other words, just take all of the points in this partition minus f of a n and so on. So that's at most. This breaks up into two kinds of things in the complement and things in the, so this is a sum over ij, f of bj minus f of aj, plus a sum over, what should I call the complementary intervals? J, the complementary intervals, f of, what are these? aj plus 1 minus f of bj. In fact, I wrote this the wrong way around, but it doesn't matter because it's an absolute value.
You could just say sum over j in each sum. Because you'll
Yes.
care about the indices.
Yes. Yes. I could. But I'm trying to make a, there'll be two different reasons why these things are small. Okay? Why is this small? All the way back here from the definition of these Vitali covers, these were made to be less than, each of these is less than epsilon times the sum of the interval times the measure of the interval. This is an epsilon and that's a sum.
Still looks like 6.
I know. You'll forgive me. Why is that small?
Absolute continuity.
Absolute continuity. This is less than epsilon. This adds up to, at most, b minus a. So the whole thing is less than epsilon times b minus a plus 1. b minus a plus 1.
But 1 is kind of weird.
Well,
Yeah.
Different kind of
so
error.
big though, you know?
This could be 100 minus.
So it could be like.
Anyway,
Over a million.
this goes to 0. Okay.
It's the epsilon. So
I know, but it's weird.
So you could do this on the positive parts and the negative parts, and now I need an exercise, which I meant to tell you
Jumping jacks? or-
well before. We're so close to done. We're so close to done. Exercise. Yes, jumping jacks. F is absolutely continuous. Implies t, the total variation up to x is, and the positive variation and the negative variation are. Okay? So if you like, if you're not happy with what we just showed is that f of b minus f of a is 0, but now take your absolutely continuous function and break it up into a positive minus a negative plus a constant. And each of these is absolutely continuous and increasing, and they don't change. That implies f is constant. Each p, f, and n, f are constant, which implies f is.
Does knowing the total variation is absolutely continuous imply the other two are absolutely continuous?
It's the same proof.
Yeah, okay.
Wait, okay, so we showed that f of b equals f of a.
And now do it for increasing functions. If it's increasing and f of b is f of a, then it's constant everywhere.
Oh. But this works for.
So start with an absolutely continuous function. Write it as positive variation minus negative variation plus a constant. Prove that each of these has, so each of these has no variation. The value at a is the same as value at b, and they're increasing. So they're constants, so the whole thing is constant. You don't like something. What don't you like? Question. Sorry.
F of x minus f of a is like written in terms of like TF, right?
Yes?
And that you can use that to show all of its constant besides the fx, and then.
Are you asking if TF is absolutely continuous, then both of these are? That's also true. Oh, no, that was Robert's question. What was your? Is that what you were?
Constant? No, to prove it's constant.
Yes.
We show that it can be written as a sum of constant things. Df, right?
Yes.
Yeah.
What were assumptions on b and a?
Nothing.
Nothing. F is a function on the interval a to
So
b.
then why isn't like the thing above just like enough?
Oh,
It is.
It is.
You just have to repeat it
There's
for every
just a-
subinterval.
You could repeat
Right.
it on every subinterval and show that the value at any 2 points is the
Just take the
same.
very first one and compare it to all the others.
Yes.
And then like.
There's a variety of, so Charlie asked about, could you do it using, are we assuming that it's increasing? You don't have to, but you also could.
Okay.
Oh,
There's a variety of ways to finish this.
So we are done?
Yeah.
We're done. We're done. We're done. We're done. We've proved that if the derivative is 0, then the function is constant. Let's prove finally let me just state, because the proof is pretty much what we've done.
Knock it out.
We're not going to get, okay, we'll do jump discontinuity next time, but let's state the fundamental theorem of Lebesgue calculus. Fundamental. So we're done. Fundamental theorem of Lebesgue integration. Okay. If f is absolutely continuous on an interval a to b, then I'm just putting everything together. F prime exists almost everywhere. Is integrable, and the integral from a to x of f prime y dy is f of x minus f of a for all x in a to b. Conversely, so this is an if and only if. So if f is in L1, then there exists a function f which is absolutely continuous, and f is f prime almost everywhere. Namely, the function f of x is equal to the integral from a to x, f of y dy will work. If you have a function that's integrable, then there is a function which is its antiderivative, and that function is absolutely continuous. And not only does it exist, but you can just write it down. You integrate f from a to x. There's a function that's absolutely continuous. We already proved that. Conversely, maybe I should have said this first. Conversely, if big F is absolutely continuous, then it has a derivative almost everywhere. That derivative is integrable, and if you integrate that derivative from a to x, you recover f of x minus f of a for every x. Fundamental theorem of Lebesgue integration, if and only if. Okay, there's basically nothing to prove. The only thing to prove is we proved that if the function is increasing, we proved that if the derivative is 0. So, proof in one line. So, f absolutely continuous implies f prime exists. Now let g of x be defined as the integral from a to x of f prime exists and is integrable. We proved integrality also. F prime of y dy, then g minus f has derivative 0, so constant.
And then plug in a.
Plug in a, and the constant is f of a. Done. So the proof, once we've done all the hard stuff, is exactly what we just said. All right, so we have to discuss jump discontinuities, which we will do on Friday, and that will be it. Any questions? Does this make sense? We have to really get into the weeds of this Vitali covering to get that nice cover for the set where we have the derivative almost everywhere. We can zoom in on those derivatives and then use absolute continuity on the rest. So absolute continuity is the right criterion for integration. It's an if and only if.